Climate change is evident. I think that's quite obvious. It's felt around the globe. The World Health Organization recently revealed that approximately 1 in 4 deaths can be attributed to preventable environmental causes. Approximately 5% of the global greenhouse gas emissions are from the healthcare sector. So in my opinion, and not just my opinion, there is an urge to reduce global greenhouse gas emissions in the healthcare sector. Obviously, we're doing anesthesia, and next to total intravenous anesthesia, volatile anaesthetics remain fundamental for delivering effective and reliable anesthesia. In the 1990s, based on the Kyoto Protocol, the global warming potential was established or was used in a 100-year frame to calculate CO2 equivalents of greenhouse gas emissions. And part of them are volatile anesthetics. However, there are an array of metrics available to evaluate climate effects on volatile anesthetics, including global warming potentials over different time horizons, atmospheric concentration, atmospheric lifetime, radiative efficiency, effective radiative forcing, and many more. There's a big discussion amongst anesthesiologists which one to use to compare volatile anesthetics. And this is quite important questions, especially in these times. And therefore, our central question in this editorial is an optimal metric for assessing climate impact of volatile anesthetics. However, I'm an anesthesiologist, and to answer this is far beyond me. Therefore, I'm very grateful that climate scientists supported this editorial, and I'm happy that amongst myself, Dr. Laube, Johannes Laube, is joining us. He's also the senior author of this editorial to give his input on this question.
The climate system itself is quite complex, and there's basically a zoo of metrics which one can use to evaluate climate impacts of greenhouse gases. And most people know about CO2 and maybe methane as greenhouse gases, but there's a whole basket of gases that also act as greenhouse gases, and among that basket are volatile anesthetics. So how do we measure their climate impact? It depends essentially on what exactly you want to know. So there are some basic metrics like atmospheric concentration, of course, or the lifetime of a substance. So how long does it remain in the atmosphere once you emit it, or once it leaks out. But these measures, they don't really grasp the climate impact very well. So there are some more advanced metrics, and the most widely used ones today are the effective radiative forcing, which takes into account the effects that mainly arise from a greenhouse gas at its current concentration in the atmosphere. And then the other one is the global warming potential, which can be taken over different time horizons or time spans, essentially. So the GWP, and they're equally important to judge future impacts on climate from a single greenhouse gas in a comparable way. So these are related to CO2 GWPs. So I would say there are many more metrics, but the ERF, so the effective radiative forcing, and the GWP, so the global warming potential, are probably the most widely used and most important ones. But there is no single metric which can capture all of the different aspects that need to be captured to properly assess the climate impact of a volatile anesthetic. Basically, I think the probably the easiest way to say this is some volatile anesthetics are simply a low-hanging fruit because they do have a high GWP. So if we continue to emit them, they might become a larger problem, even though they might not currently be one. And they are easy to replace. But I think Mark will say a little bit more about that. So that is probably the perhaps the most important message is some volatile anesthetics are more problematic than others, even though all of them are currently at very low concentrations. But if we just simply say there is no problem, we might generate one in the future by simply using more. And in this case, in this particular case, avoiding the worst ones is relatively straightforward.
First of all, I think we always need the span. We have total intravenous anesthesia, in my opinion. We always will also need volatile anesthetics. However, we have a choice of volatile anesthetics, and what we just heard and looking at all the metrics also mentioned in our editorial, it's quite obviously that one of them, that's desflurane, has a higher impact, and replacing it would be a straightforward, Johannes, as you said it, a low-hanging fruit to reduce climate impact. I think that's an important clinical take-home message. The second clinical take-home message, in my opinion, is if we use volatile anesthetics, no matter which one, they should be administered in minimal flow. And we need to be flexible, as always, and we develop ourselves, science develops, and we really have to reassess the whole process continuously. And we have life cycle assessments, for example. All this has to be taken into account to optimize not just our clinical approach and for the best treatment of our patients, but also considering the environmental impact we have. And therefore, I think hopefully this editorial will help to give a good guidance which volatile or which metrics to use to really choose our volatile anesthetic with this information. Obviously, first point is clinical impact, patient safety, but then to use this information.